Hi everyone. In this video we're going to be talking about inconsistent and dependent systems of linear equations. And I started talking about this a little bit in the last video when we were graphing systems of equations. And you'll recall from the last video that if we were to look at a coordinate plane, oh, that's pretty rough. Let me do it a little better than that. So if we had, well, not much better, but if we had an x and a y-axis, this is a coordinate plane, and we had a line like this and a line like this, we talked about how that spot where they intersect, right here, would be the unique solution. Unique solution to that system of equations. If you look at this graph, never again are those two lines going to cross. So that means that there's only one spot, looking at these two graphed lines, where there's a coordinate that falls on both lines. And that happens to be right where they cross each other. That point, that coordinate, would be on both of the lines. And we also talked in the last video about how if we had the same slope, oh, that's a bad one again. Let me see if I can do better. All right, so we have an x and a y, and I'm not going to be able to draw these perfectly, but what if my lines were perfectly parallel? If they're perfectly parallel, we can do this symbol here, and single arrow pointing both ways on it. That would mean that those two lines are parallel. That's a math symbol to note that. So if these two lines were parallel to each other, doesn't matter how far we would go up or down, they would never cross each other. And if they never cross each other, that means that there's absolutely no place where the same coordinate would fall on both lines, meaning that this system of equations would have no solution. And what we call that is an inconsistent system of linear equations. So inconsistent equations. That just essentially means that they do not have a solution. There's no solution to it because those lines are never going to cross. And then we have one other type here. Let me see if I can draw decent straight lines the first try. Well, that'll be good enough. We have an x and a y. And in this case, I'm going to draw two different color lines. My first line is going to be red. And my second line, let's see how I do here, is going to be green. And you'll notice I drew the lines right on top of each other. These are the same exact line. And if they're the same exact line, then they're going to have infinite solutions. And we call that a dependent system of equations. Dependent system of equations. That just means infinite solution. So you can think of this one as infinite solutions. And you can think of this one as no solution. And you can think of this first one as one solution. But the words we use for one solution are unique solution. The word we use for no solution is inconsistent equations. And the word that we use for infinite solutions is dependent system of equations. So now that we know what these graphs look like, let's take a look at how algebraically we can solve these and determine how many solutions there are to a system of equations. So let's find some space here. And I'm just going to write out an equation. So let's start with this. So far, a lot of the equations we've looked at have worked out this way. Let's say x plus y is equal to 6, and 2x plus y is equal to 8. Well, I would look at this system and I would say, let's subtract them, because my y's here are already the same, right? So same subtract, x minus 2x is negative x, y minus y cancels out, and then 6 minus 8 equals negative 2. And then I can divide both sides by negative 1. My negative cancels out, and I have x equals 2. Now I can use that 2 to plug it back into either equation. In this case, I'm going to go up to this top equation. We're going to plug in 2 for x, so 2 plus y equals 6. Now I'll subtract 2 from both sides, and I get y is equal to 4. So we have x is equal to 2, and y is equal to 4. Though that solution is a unique solution. This is no different than the ones that we've been doing all along this unit. When we get down to the end of our system of equations, we solve for one variable and then we can solve for the other. That tells us that 2 and 4 for x and y make both of these equations true. Therefore, it's a unique solution. This is a normal system of equations. 2 lines that are going to cross in one spot. Let's try a different one and see what that one might look like. Let's try this one. 2x, that's not a pencil. Hold on a second, there we go. 2x plus y equals 1. And let's try 4x plus 2y equals 4. All right, when I look at this one, I'm going to use elimination again. My y on top, if we look here, if I were to multiply the top by 2, the top equation by 2, I could have 2y and the top and the bottom, and I could get those to cancel out. So I'm going to multiply this top equation by 2, and my new equation is going to be 2 times 2x. Remember, I'm going to multiply this by everything. So 2 times 2x is 4x. 2 times 2y is positive 2y, and that's equal to 2. So now I have 2 equations. I have 4x plus 2y equals 4, and 4x plus 2y equals 2. My 2y's are the same, and so I'm going to subtract 4x minus 4x. Well, that cancels out. And 2y minus 2y, well, that cancels out. So I'm left with 0 on the left side, and that's equal to 4 minus 2 equals 2. Well, what do you notice happened? My 4x's were the same, and my 2y's were the same. So both of my variables canceled out, and I don't have any variable left. So I'm left with 0 on the left and 2 on the right. And that's not true. 0 is not equal to 2. And I don't have a variable that's equal to anything. I couldn't get to that point. And so I'm going to say 0 is not equal to 2. And what that means is that there is no solution to this system of equations. The word we use for that, remember we said, is inconsistent. This is an inconsistent system of equations. Okay, so this is my answer, inconsistent. And the reason we knew that, the reason that was different than the last one we did, is in the last one, we were able to get to a variable is equal to a number, and a variable is equal to a number. But in this case, we didn't have any variables left, and the statement that we were seeing here, 0 equals 2, is not true. 0 can never equal 2. So therefore, it's an inconsistent equation, and that's what you're looking for to know. So remember, an inconsistent equation, that's parallel lines, right? That's what we just found. And the indicator for that algebraically was a false statement that we were left with at the end, where we just had numbers left, and it wasn't true. All right, let's try another one here. let's do this one. Let's do x plus 2y is equal to 2. And let's do 2x plus 4y is equal to 4. Well, again, on this one, I'm going to use elimination. I can see that on the top equation here, if I were to multiply by 2, my x would become 2x, just like the 2x on the bottom. So I'm going to distribute this 2 to everything in the top equation. And I get 2 times x is 2x, plus 2 times 2y is 4y, and then 2 times 2 is 4. And you guys may already be seeing what's going to happen here, but I'm going to play it out as if I don't know. So I have the same term on top and bottom, 2x and 2x. So I'm going to subtract. 2x minus 2x cancels out. 4y minus 4y, oh, that one cancels out too. So I'm left with 0 on the left, and that's equal to 4 minus 4, which is also 0. So here we have 0 equals 0. I don't have any variables. My variables canceled out again. But you'll see that what I'm left with is actually a true statement. This is true, right? 0 does equal 0. And since 0 does equal 0, that means that we actually have infinite solutions here. We call this dependent systems of equations. So I'll put my box around dependent. These are dependent equations. And what you may have noticed is that here 2x plus 4y equals 4 and 2x plus 4y equals 4 were the exact same equation. Right? That's why they canceled out to a true statement at the end. It doesn't matter what you put in for x and what you put in for y. You're always going to get the equation to be true. And we know that that is the case because we ended with a true statement. These two equations being the exact same equation, where am I here? That is this scenario, right? That's the same exact equation. If we put the same equation twice into the Desmos graphing calculator, it's going to put two lines on top of each other. They're the exact same line. Therefore, they have infinite solutions and they're dependent equations, right? So what you'll notice is unique solution ends with a variable is equal to a number, and then we can find the other variable is equal to a number. Inconsistent and dependent equations both end without a variable, right? They both end with numerical statements. In an inconsistent system of equations, that's a false statement. 0 does not equal 2. In a dependent system of equations, that's a true statement. 0 does equal 0 here. And that's what you'll find on all of these. And sometimes you may know, obviously, if we were to look up here and we saw that 2x plus 4y equals 4 is the same equation as 2x plus 4y equals 4, you might already know these are dependent. I don't have to go all the way through and solve it. You may find, though, that at least until you get really comfortable with these, you do want to solve it, because sometimes they can throw you off just enough. Like if the top one was 2x plus 4y equals 4, and the bottom one was 2x minus 4y equals 4, those aren't exactly the same equation, and you'll want to play those out and see what you get for a solution. But let's take a look at a few more examples like this and see how we do with them. Let's try this one. Let's try 11x plus y equals 2, and 22x plus 2y equals 3. And I'm going to solve this one using substitution. Even though it's set up pretty nicely for elimination, I just want to vary the way that I solve these so that you guys can see you can solve them either way. And what I see here is that I have a y that's by itself. And so if I were to get rid of the 11x up there on the same side of the equation as the y, well then I'll have an equation set up really well for the substitution method. So let's take this equation here and let's rewrite it. So I have 11x plus y equals 2, and I want to subtract 11x from both sides, and I get the equation y is equal to 2 minus 11x. Well, now I have two equations that I'm going to use. I'm going to use this equation here and this equation here, and wherever I see a y in the top equation, so right here a y, I'm going to plug in 2 minus 11x. So let's rewrite this. The top equation says 22x plus, and then I can rewrite, I'm going to write plus 2y instead of y. I'm going to write 2 minus 11x, just like we have down here, and then that's equal to 3. So I hope everyone's with me, sees how I got that in there. I used that top equation and I plugged in 2 minus 11x for y. And now I have a one variable equation. Let's solve this equation. We're going to start out by distributing. So I have 22x plus 2 times 2 is 4. And then I have 2 times negative 11 is negative 22x equals 3. Now I need to find my like terms. 22x minus 22x. That's 0. Those cancel out. So I have 0 plus 4 equals 3. 0 plus 4 is just 4. That's equal to 3. And I don't have a variable anymore. And I'm left with a number being equal to a number. And is that true? Does 4 equal 3? It doesn't. So what I have here, I'm going to put this line through the equal sign to say 4 does not equal 3. What I have here is an inconsistent system of equations. Right? If you remember, that means that it's inconsistent when our variable drops out and the statement is false. And an inconsistent system of equations means that those two equations have the same slope, but they have different y-intercepts, so they're parallel to each other, and they're never going to touch. Let's do another one. Let's try the equations 3x equals 3 minus 3y. And then x plus y equals 1. Let's see, I'll solve this one using substitution again. What I'm going to do is I'm going to get this y on the bottom by itself by subtracting x from each side. And my new equation is y equals 1 minus x. Wherever I see a y on the top, I'll plug in 1 minus x. So the top equation says 3x equals 3 minus 3y. Instead of y, I'm going to write 1 minus x. And now I'm going to distribute and solve this equation. 3x equals 3. Negative 3 times 1 is negative 3. And then negative 3 times negative x is positive 3x. And now I want to solve my system of equations here. So this equation, I'm going to try to get all of my variables to the same side. So let's see, I am going to subtract 3x from here. I'm going to do the same from this side. Well, those all canceled out, so I have 0 equals 3 minus 3. 3 minus 3 is 0, so I have 0 equals 0, which means my variables are gone, but that's actually a true statement. 0 does equal 0, which means that I have a dependent system of equations here. Means that it has infinite solutions. They are the same line, right? Let's do one more here. Let's use the equations 2x plus 3y equals 29 and 2x minus 17 equals y. Well, what you might notice right away here is that this is already solved for y in terms of x. So anywhere that I see a y in the top equation, I'm going to plug in 2x minus 17. So my new equation would be, working from the top equation up here, would be 2x plus 3 parentheses, and now I'm going to plug this in. 2x minus 17 is equal to 29. We're going to distribute and solve this equation. So I have 2x, positive 3 times 2x is plus 6x. And then I have positive 3 times negative 17, which is going to give me negative 51. That's equal to 29. Now I'm going to combine like terms. 2x plus 6x equals 8x minus 51 equals 29. Now I'm going to add 51 to both sides. That cancels out, and I have 8x is equal to 29 plus 51 gives me 80. And now I need to divide both sides by 8 to get x by itself. And I have x equals 80 divided by 8, which is 10. Now that I have 10 for x, that's one of my answers. I need to plug in 10 for x. I'll do it with this equation here. So that's 2x, or 2 times 10 minus 17 equals y. 2 times 10 is 20. Bring down the minus 17 equals y. 20 minus 17 is 3 is equal to y, which means y equals 3 and x equals 10. So that means that these equations have a unique solution, right? You don't have to write this for unique solution, but I'm going to write it just to remind you. That's the terms that we use, unique solution. And think about it for a second. If a unique solution means that these equations cross each other when graphed, at what coordinate, what point would these equations cross? Well, a coordinate is written as an x comma y, and in this case x is 10 and y is 3. That was our unique solution. So these equations are going to cross at the point 10 comma 3. All right, so this is inconsistent, dependent, and unique solution system of equations. And I hope that you can see what it looks like algebraically, right? Just to recap really fast, a unique solution, let's see, I'll use yellow here, I don't use yellow very often. A unique solution gives us a variable is equal to a number, and then we can use that variable to, that value for that variable to plug into one of the equations and find the other variable. So unique solution ends with x and y being equal to numbers. A dependent system of equations, that's the same exact line graphed on top of itself, right? Algebraically, we see that where the variables both drop out, they cancel out of the equation, and we're left with a true statement like 0 equals 0 or 5 equals 5. And then an inconsistent system of equations, these would be parallel lines. They have the same slope but different y-intercepts. And algebraically, we see that when the variables, just like a dependent system of equations, the variables drop out, they cancel out, and we're left with a statement with just two numbers, but the statement isn't true. Like 4 does not equal 3, right? So that would be inconsistent, dependent, and unique solution systems of equations. As always, please reach out if you are confused on anything or have any questions. Get to your practice, and I will see you in the next video.